In this section, we're going to be dealing with calculations based on the equilibrium constant. So given some information about a reaction, usually the concentrations of starting materials and the equilibrium constant itself, how can we determine the concentrations of all of the reactants and products once the reaction has reached equilibrium? So when doing these types of calculations, we're going to set up a table which is commonly known as an ICE table. The I represents the initial concentrations or partial pressures of the reactants and products. The C represents how they change, how much we will lose from the reactants, how much we will gain from the products. And the E equals the equilibrium values, whatever those might be. So first I'll show you how to set up the ICE tables, and then I will go through a bunch of worked examples. So given this reaction, nitrogen and oxygen producing nitrous oxide, normally in these types of questions we'll be given initial concentrations. So we give initial concentration of nitrogen, an initial concentration of oxygen, and an initial concentration of our product, which we're saying is starting at 0. So we're starting this reaction only with reactants, and we're going to let it proceed to equilibrium, and then we need to know how much N2, how much O2 remains at equilibrium, and how much NO gets formed. The only other information we'll be given, in this case, is the equilibrium constant Kp. So again, we're asked, what are the partial pressures of reactants and products when the system achieves equilibrium? So the first thing we do when we set up an ICE table is to write out the chemical reaction. And sometimes I would put that also up on this part of the table here, right at the top. So the next step is to write the initial concentrations or partial pressures of each of the reactants and products. So in this case, the partial pressure of N2 was 0.79 atmospheres. The partial pressure of O2 was 0.21 atmospheres. And the partial pressure of NO was 0. Okay, so we're just setting up the initial partial pressures that are given in the question. The next step is to show how these are going to change. Now we don't know exactly what's going to happen. We know we're going to lose some reactant and we're going to gain some product. So we show that by writing minus x's for reactants that we're losing. And since each of the reactants has a stoichiometry of 1, it's just going to be a minus x for the reactants. Now since we have a 2 for our product, we're going to be adding 2x. Okay, so again, x is just a variable to denote how much of the reactants we're going to lose and how much of the products we're going to gain. Now we know this reaction has to shift to the right because we don't have any products yet. So the concentrations of reactants are going to decrease and the concentrations of the products are going to increase. To finish off the table, we're going to express the equilibrium conditions. So the equilibrium conditions are simply what we start with minus what the change is. So in this case, 0.79 minus x is what's going to happen to the N2. We're going to have 0.21 minus x for the oxygen, and our NO, that's going to increase by 2x. So once we figured out this table and set it up, the only part we have to worry about is the equilibrium conditions. So then what we're going to do is to write out the equilibrium expression for this reaction. So here we have Kp equals the partial pressures of the products divided by the partial pressures of the reactants. And remember, don't forget the 2 from the stoichiometry. After that, we simply plug in the equilibrium conditions into our equilibrium expression. So the partial pressure of NO is 2x, but that whole thing was squared, so we have to include the 2. And our partial pressure of N2 was 0.79 minus x, and our partial pressure of O2 was 0.21 minus x. After we do this, then we simply have to solve for x. Now in this case, if we were to multiply this all out, we would end up getting a quadratic formula, and we'd have to use the quadratic equation in order to determine what the value of x is. You would get a positive value for x, a negative value for x, but remember what x is supposed to represent. So just let me go back to the table for a second. And notice that all of these columns are in units of atmospheres. They'll either be a pressure unit or a concentration unit. So when you solve for x, x is going to represent a partial pressure in this case. If we were talking about concentrations, x would represent a concentration. So if x is a concentration or a partial pressure, we know that that has to be a positive number. So when we solve for the quadratic formula, we will take the positive number that we get out of that equation. Once we know what x is, then we can determine what the partial pressures of each of oxygen, nitrogen, and NO are at equilibrium. Now, there are conditions that we could use what are called simplifying assumptions. And that happens when the value for the equilibrium constant is very small, such that the reaction is very reactant favored. Remember, a small equilibrium constant means the reaction mostly stays with reactants and only very few products are formed. I do have some examples coming up that use the simplifying assumption, and I will further explain it when we get there. So this slide just shows the steps that you have to go through when solving these types of calculations. So the rest of this video is going to be dedicated to going through some of these equilibrium problems. So let's try this one first. So at equilibrium, there are 2.5 moles of H2, 1.35 times 10 to the minus 5 moles of S2, and 8.70 moles of H2S in a 1 liter vessel. Calculate Kc for the following reaction. And we don't need an ice table for this one. Okay, we're asked to find the equilibrium constant. We are given concentrations at equilibrium. Okay, so it says right here, at equilibrium. So if something is already at equilibrium, we don't need to try and find the concentrations at equilibrium. And that is the whole point of an ice table. Ice tables are used when we're given initial concentrations and we're asked to find equilibrium concentrations. But we already have them, and we're only asked to find the equilibrium constant in this case. So all we have to do for this one is to write out the equilibrium expression. So Kc is going to equal the concentration of H2S squared divided by the concentration of H2 squared times the concentration of S2. And if we substitute in the values, we'll have 8.70 molar squared divided by 2.50 squared times 1.35 times 10 to the minus 5. So then Kc is going to end up equaling 8.97 times 10 to the 5. Okay, so that's about as simple as I can get, already giving you equilibrium concentrations, only asking you to find what the equilibrium constant is, and remember, equilibrium constants don't have units. Okay, so here now is a question where we are asked to find equilibrium concentrations. So we're given initial concentration of Hi and its equilibrium constant and a chemical equation. So we're not given a lot of information, but we can still determine what the equilibrium concentrations are using an ice table. So let's set that up. We're going to have 2Hi in equilibrium with H2 and I2. And if we set up the ice table, we have an initial concentration of Hi as 0.100 molar. And our H2 initially is 0, and our I2 initially is 0. Now, how is this going to change? Well, we're going to lose 2 x's from the Hi because it has a stoichiometry of 2. We're going to gain an x for H2, and we're going to gain an x for I2. So at equilibrium, we're going to have 0.100 minus 2x for Hi, x for H2, and x for I2. The next step is to write out the equilibrium expression. So Kc equals the concentration of H2 times the concentration of I2 divided by the concentration of Hi squared. Now if we fill in the equilibrium expression using the equilibrium conditions here as well as the Kc, we end up with 0.11 equals x squared divided by 0.100 minus 2x squared. Now, since we have two terms that are squared on the right-hand side, if we simply take the square root of both sides of that equation, the 0.11 and the x squared divided by the 0.1 minus 2x, then we can get rid of the squareds and make our life a little bit easier since we won't have to worry about a quadratic formula. So if we take the square root of 0.11, we end up with 0.33166, and so that's going to equal x divided by 0.100 minus 2x. And if we continue to multiply that out, 0.33166 times 0.100 minus 2x equals x. 0.033166 minus 0.66322 x equals x, and then solving for x equals 0.0199. And remember, this x represents a concentration, so this is going to be molar. And now, since we know the value of x, we can use that to determine the concentrations of reactants and products by using our equilibrium conditions here. So we just substitute our value for x into x's in the equilibrium conditions above. So the concentration of H2 is going to equal the concentration of I2, which is going to equal 0.0199 molar, because that's just simply x, and the concentration of HI is going to equal 0.100 minus 2x, so then that equals 0.0602 molar. So these are our two equilibrium concentrations of our reactants and our products. Now we can do one extra thing just to check whether or not our answer is correct or not. So I'm just going to do it in this little box here. So if we substitute our values back into the Kc expression, we should be able to get the same equilibrium constant as long as our concentrations were calculated correctly. So let's go Kc equals 0.0199 squared, so that's our I2 and our H2, divided by 0.0602. That's also squared because Hi is squared. So if we solve that, Kc ends up being 0.109, which is pretty close to the 0.11 that we were given in the question. Okay, so let's go through another example. Initial concentration of PCl5 is 0.1 molar, and Kc is 1.3 times 10 to the minus 5 for the following reaction. Calculate the equilibrium concentrations for each species in the reaction. So again, we're not given much information. We're just given an initial concentration of a reactant and an equilibrium constant. So first, let's set up the ice table. So we're going to have PCl5 in equilibrium with PCl3 and Cl2. Our initial concentration, our change, and our equilibrium condition. So initial concentration of PCl5, 0.01 molar, PCl3 0, Cl2 0. We're going to lose some PCl5, we're going to gain some PCl3, and we're going to gain some Cl2. Since our stoichiometry is only 1 for each of the reactants and products, we don't need any more than a minus x and a plus x in our change row. Now our equilibrium condition, 0.100 minus x. For PCl3 is x, for Cl2 is x. Next step, write out the equilibrium expression. Kc equals the concentration of Cl2 times the concentration of PCl3 divided by the concentration of PCl5. Now if we substitute in the values, 1.3 times 10 to the minus 5 equals x squared over 0.100 minus x. Now in this case, if we were to multiply this out and solve for x, we would end up with a quadratic formula. So we would have to use the quadratic equation in order to determine what x is. But since our equilibrium constant k is really small, so small enough such that the reaction here is not going to produce very many products, right? Because a small equilibrium constant means it's reactant favored, so it's mostly going to have PCl5 remaining and will not make too much PCl3 or Cl2. So what we can do is assume that this x in the equilibrium condition is negligible, so we can ignore it, and that means that we can ignore this x down here. And that ends up simplifying everything so we don't have a quadratic formula at the end. So if we continue on with the math, 1.3 times 10 to the minus 5 times 0.100 equals x squared. And then if we solve for x equals 1.14 times 10 to the minus 3. And again, that's a concentration, so molar. So to report the concentrations of reactants and products, again, we simply look at the equilibrium line to determine what we have to do. So PCl3 and Cl2 are simply just x, and that's what we solved for. So this is going to equal the concentration of PCl3 and Cl2, and the concentration of PCl5. Since we assumed x was negligible up here, then we don't have to subtract x from our concentration. So the concentration of PCl5 is simply 0.100 molar. Now I want you to think about what the concentration of PCl5 would be if we had subtracted 1.3 times 10 to the minus 5. So look how many decimal places we have there. Right? This digit here is the 10 to the minus 3 digit. So if we were to subtract 1 times 10 to the minus 5 from this number, we would be subtracting a number that is much smaller than the 0.1. And it would still just round up to 0.1 anyway. So that's why we can assume that that x that I crossed out above is negligible, because when we try and subtract it from our initial concentration, it actually doesn't make a difference. Okay, so let's try another one. In an experiment, 1 mole of N2O4 is placed in a 10-liter vessel and is allowed to react as described below. Calculate the concentration of each species at equilibrium. So same process as before. Let's do the ice table. N2O4 in equilibrium with 2NO2. Set up the ice table. Initial concentration. Well, we don't have a concentration this time, but we can calculate it because we have moles and we have liters. So if we take 1 mole divided by 10 liters, we get 0.100 molar. And we initially started with 0 NO2. We're going to lose some N2O4 and we're going to gain 2x of our NO2. So our equilibrium condition, 0.100 minus x, and for NO2 is going to be 2x. Now we write the equilibrium constant expression, Kc equals the concentration of NO2 squared divided by the concentration of N2O4. Plug in the values, 4.0 times 10 to the minus 7 equals 2x squared divided by 0.100 minus x. Now we have the same situation as we did in the last example. We have a very small equilibrium constant. In fact, it's even smaller than the previous example. So if we could assume this x was negligible then, we can assume it's negligible now. So we'll just ignore that x there, and we'll continue on multiplying everything out. So we'll have 4.0 times 10 to the minus 7 times 0.100 equals 2x squared ends up being 4x squared. So 4.0 times 10 to the minus 8 equals 4x squared. So then 4.0 times 10 to the minus 8 divided by 4, take the square root, that's going to equal x, and then x equals 1 times 10 to the minus 4. Again, molar because it's a concentration. So now we have to report the concentrations of each of the reactants and products. So we have a concentration of N2O4. It was 0.100 minus x, but we're not considering that minus x. So the concentration of N2O4 equals 0.100 molar. And then the concentration of NO2 is going to equal 2x. So that's going to equal 2 times 1 times 10 to the minus 4, which ends up being 2 times 10 to the minus 4. And these are both going to be concentrations. Now, I didn't do this in the last example. I'm not going to do it in this one either, but if you take the concentrations that we calculated, so the 0.1 molar and the 2 times 10 to the minus 4 molar, and put them back into the equilibrium expression up here, and solve for Kc, the Kc value that you get from the concentrations you calculated should equal the Kc value that's given in the question. Again, if you get that number, then you have done it right. If you don't get that number, then something in the math is wrong, and you should go back and check your work. Okay, so here's the last example I'm going to go through, and the one difference with this one is we are given concentrations of everything, not just the reactants. So we don't even know which way the reaction is going to proceed. Remember in the last section we talked about Q, which is going to tell us whether or not the reaction needs to proceed in the forward direction or in the reverse direction to reach equilibrium. So determining Q and which way the reaction goes is going to determine how we write our equilibrium expression. If Q ends up being smaller than K, then the reaction will proceed in the forward direction. And if Q ends up being bigger than K, then the reaction will proceed in the reverse direction. So here we go. We're trying to figure out the equilibrium concentrations of the 4 gases, and given the initial concentration of 0.05 molar for each one of them. So again, set up the ice table. We have CO plus H2O in equilibrium with CO2 and H2. We'll do the initial concentrations for now as 0.05 for each one of them. Right, remember, those are molar concentrations. Now, before I go on, I'm going to calculate Q to see whether or not this reaction is going to be going in the forward direction or the reverse direction. So again, Q is calculated when we don't know whether or not the reaction is at equilibrium, but we can still use the concentrations that were given to determine what Q is. So Q is going to equal the concentration of CO2 times the concentration of H2 divided by the concentration of CO times the concentration of H2O. And so that's going to end up being 0.050 squared divided by 0.050 squared, and that equals 1. So in this case, since our Q is 1 and our Kc is 5.1, QC is less than Kc, so the reaction is going to go in the forward direction. So let's continue on with the ice table. So our change is going to be minus x, right? Remember, those are now reactants. We know that for sure because the reaction has to go forward. So our products are now going to be plus x and plus x. So each of these equilibrium conditions, 0.05 minus x, 0.05 minus x, and for products 0.05 plus x, and 0.05 plus x. Now we continue on as usual, write the equilibrium expression, which is going to be the same as Q up here, right? It's still the products over the reactants. So I'm just going to write in the equilibrium conditions right away. So we're going to have 0.050 plus x and there's a couple of them, so that's going to be squared. And then the bottom, we're going to have 0.050 minus x, and that's also squared. Now the Kc, we're given that value of 5.1. So 5.1 is going to equal the equilibrium conditions. Now, just like in the second example, since we have the numerator and denominator both squared in this expression, we can just take the square roots of both sides. So if we take the square root of 5.1, we get 2.258 equals 0.050 plus x divided by 0.050 minus x. And if we multiply everything out, 2.258 times 0.050 minus x equals 0.050 plus x. Continuing on, 0.1129 minus 2.258x equals 0.050 plus x. Collect some of our terms. 0.1129 plus 0.050 equals 3.258x. And if we solve for x, x equals 0.0193. Okay, so again, our equilibrium conditions are here. So for the reactants, we have to subtract our calculated x value from the 0.05. So the concentration of CO is going to equal the concentration of H2O, which is going to equal 0.05 minus 0.0193. So that equals 0.031 molar. And the concentration of CO2 equals the concentration of H2, which equals 0.05 plus 0.0193. So that ends up being 0.0693. And that's a molar concentration. So again, if you want to check to see if these concentrations are correct, take the concentrations that we just calculated, insert them back into the equilibrium expression, and if you get the same Kc value out that is in the question, then you have done the math correctly. So that's all I have for this video. If you have any questions, please let me know.